Okay, let's just jump right into it. There's a brand new AI model entering the world of tropical cyclone forecasting that, frankly, could be absolutely huge for predicting these incredibly dangerous storms.
Mm-hmm.
But, and this is a big but, if it performs well in real time this season.
That's the key test right there. Absolutely.
Welcome, everyone, to Meteorology Matters. This is where we really try to take an in-depth look at complex information, sort of unpack it, and help you get informed quickly and, well, thoroughly.
Yep, cutting through the noise.
Today, we're diving into something really fascinating and, honestly, often frustratingly difficult. The science of forecasting tropical cyclones.
You might know them as hurricanes, typhoons, cyclones. Depends where you are.
Exactly. And we're exploring how artificial intelligence, AI, is now being applied in some, well, experimental ways, but ways that could potentially revolutionize how we tackle this huge challenge.
We're looking at some genuinely promising new approaches here, stuff that could really represent a leap forward in how accurate our predictions can be.
Just, take a second and think about the sheer power of these storms, the impact they have.
Oh, it's immense. The danger, the destruction.
And the cost. We were looking at some figures, an estimated $1.4 trillion in economic losses globally, just in the last 50 years.
It's almost hard to wrap your head around a number like that.
It really is. And behind that number, you've got countless lives disrupted, communities just devastated, long, hard roads to recovery.
Yeah.
And that really highlights why accurate warnings, why preparedness aren't just, nice-to-haves. They're absolutely vital.
Life or death, often.
Totally. The earlier and more precisely we could figure out where these things are going, how strong they'll get, that directly translates into protecting people, securing property, saving lives.
Right.
That's the whole point, right? That's the motivation behind all this forecasting work.
And improving that forecasting, well, it's a serious scientific hurdle. Tropical cyclones aren't simple weather systems you can just, plug into a basic formula.
Right. They're beasts.
They really are. They're vast, complex atmospheric engines. They're fuel, primarily warm ocean water.
Like giant heat pumps almost.
That's a great analogy, actually. Giant swirling heat pumps. They take heat and moisture from the sea surface, pull it way up into the atmosphere, and that drives this intense convection. Those huge thunderstorms spiraling around the core.
And the scale is just massive.
Huge. The strongest winds are near the center, yeah, but dangerous conditions can stretch out for hundreds of miles.
So what makes them so hard to forecast accurately? You said it's a hurdle.
Well, a big part of it is their sensitivity. They're incredibly finely tuned systems, their behavior, where they go, how strong they get. It's critically dependent on even really subtle differences in the atmosphere around them.
Like what kind of differences?
Oh, a small shift in a steering current way up high, maybe miles away, a tiny change in how fast the ocean underneath is warming up, even just interacting with land if they get close. Any of these seemingly small things can cause a pretty dramatic change in the storm's path or, how quickly it spins up or weakens.
Okay, so you have this massive, powerful, but also really sensitive system moving through an atmosphere that's constantly changing anyway.
Exactly. That inherent complexity, that sensitivity, it's a big reason why the traditional forecasting models, the physics-based ones that are the workhorses today, have always faced this kind of fundamental trade-off.
A trade-off in trying to predict everything about the storm.
Yeah, exactly. Can you maybe break down what that sort of dual nature of forecasting means for these models?
Sure. So these physics-based models, they're built on, well, fundamental physical laws.
The equations.
Right. That simulate how the atmosphere, the ocean, the land surface behave.
They create like a virtual Earth, basically, and run time forward to see how weather evolves.
Right. But the problem is you can't model the entire planet down to every tiny detail simultaneously. Not if you want the forecast, now, not next week.
Yeah.
The computing power just isn't there for that kind of real-time operational need.
Even with today's supercomputers, yeah, you hit limit.
So the model builders, they have to make choices, big choices,
Yeah.
especially about resolution, how detailed the model's view is.
Okay.
So predicting the cyclone's track, right, where it's generally going to go over several days, that's mostly determined by the big picture stuff. The large-scale atmospheric flow, these huge currents of air high up, that basically steer the storm along.
Like rivers in the sky pushing it.
Exactly. So to capture those global steering currents properly, you need a model that covers a huge area, ideally the whole globe.
A global model.
Right. But because it's global, it has to have lower resolution.
Okay.
It sees the atmosphere in bigger chunks, maybe grid boxes tens of kilometers wide. It gets the forest view, The overall flow, which is great for predicting the track.
Makes sense. Global view for global steering.
But then there's the intensity. Is it going to stay a tropical storm or blow up into a major Category 4 or 5 hurricane?
The million-dollar question, often.
Right. And that depends on incredibly complex, really small-scale things happening inside and right around the storm's core. The eye wall. We're talking about how air is rising and sinking in these intense thunderstorm bursts, how moisture is cycling through, the turbulent winds mixing near the surface, how the storm is interacting with the ocean right below it, even the friction from waves. Tiny details, relatively speaking.
Stuff happening on a much finer scale than those big steering currents.
Exactly. And to simulate those intricate details, you need models with really high resolution. Models focus specifically on the storm and its immediate surroundings.
So regional models.
Typically, yeah. Regional models. They cover a smaller area, but their grid boxes might only be a few kilometers wide. They can see the trees, maybe even the leaves, of the storm's internal structure, which you need for intensity.
Okay, so global, lower resolution for the big picture track, and regional, high resolution for the small scale intensity details.
Yeah.
That's the trade-off you mentioned.
That's the classic trade-off. You generally can't have one physics-based model that does both optimally, especially not fast enough for operational forecasting.
Why not? I mean, why can't you just run a super high-res global model?
Just too slow, too computationally expensive. To run fast enough to be useful in real time, physics models have to make approximations.
Okay.
You can build that global model, but its resolution will be too coarse, too fuzzy to really capture those fine details driving intensity accurately.
All right, it misses the leaves.
And you can build that high-resolution regional model focusing on the storm. But two problems. One, it still needs information from a global model at its edges to know how the larger environment is pushing it around, the boundary conditions.
Okay. It needs the big picture context.
And two, its high resolution still makes it too computationally demanding to run for the whole globe. So what operational centers usually do is run a whole suite of different models.
Right, you see those spaghetti plots sometimes.
Exactly. That often comes from ensemble systems where they run the same model maybe 20, 30, 50 times with slightly different starting conditions to get a range of possibilities. Plus, they look at different global models, different regional models.
Trying to piece together the best possible forecast from all these different tools.
Precisely. But it's been this persistent challenge, getting truly state-of-the-art accuracy for both track and intensity at the same time from a single physics-based system because of those computational limits and the different scales of physics involved.
Which brings us back to why any improvement matters so much.
Absolutely. When a storm's bearing down, knowing if it's going to hit 50 miles further north or if it's suddenly going to ramp up in strength just before landfall, that makes a world of difference.
For evacuations, for staging resources, for just telling people how serious the risk is.
It really does. Better predictions directly save lives and cut down on that staggering economic damage we talked about. Every kilometer closer on the track, every knot more accurate on the intensity.
It translates into better decisions on the ground, which is why this new development we're talking about is getting so much buzz. It's a fundamentally different way of tackling the problem.
All right, let's dig into that, this different approach. Tell us about this new experimental AI-based tropical cyclone model. What's the story here?
Okay, so this comes out of a collaboration between Google DeepMind and Google Research. And the key difference is, unlike those traditional models trying to explicitly calculate physics equations,
Right.
this AI model learns directly from massive amounts of historical weather data. The source material we looked at says it's based on something called stochastic neural networks.
Stochastic neural networks. Okay, that sounds technical. Can you give us the simpler version? What does that actually mean for forecasting?
Sure. Think of neural networks at a basic level as really powerful pattern recognition machines. You train them on enormous data sets, and they learn complex relationships and patterns within that data.
Without being explicitly told the physics equations.
Kind of, yeah. They learn the correlations, the cause and effect relationships as reflected in the data itself. Now, the stochastic part, that basically means it involves probability or randomness. So in this context, it means the model is designed to handle the inherent uncertainty in weather. Weather isn't perfectly predictable, right? So a stochastic model doesn't just spit out one single answer. It can generate a range of possible outcomes.
Like those ensemble models you mentioned.
Exactly. It reflects the probabilistic nature of the atmosphere. So it's a sophisticated type of AI that's particularly well-suited for trying to model chaotic, dynamic systems like weather. It learns the patterns and acknowledges the uncertainty.
Got it. Learning patterns from data, handling uncertainty, giving multiple possibilities. So how does this AI approach claim to get around that classic trade-off, being good at both track and intensity in one system?
Well, this is really the core innovation they're highlighting, and it's kind of the aha moment. This experimental AI model is designed as a single, unified system.
One model for both.
That's the goal, yeah. Aiming for state-of-the-art accuracy for both track and intensity predictions simultaneously. Instead of being limited by the computational cost of simulating high-resolution physics everywhere.
Like the traditional models.
Right. This AI model, through its training on all that data, seems to be capable of learning the really complex interplay between the large-scale atmospheric patterns that steer the storm.
The forest view.
And the fine-scale internal dynamics that control its intensity.
The leaves view.
Exactly. It appears to learn these connections directly from observations across all those different scales, rather than having to explicitly simulate the physics with different resolutions for different aspects. It's just a different way of modeling the problem.
That does sound like a potential way around those computational bottlenecks. Learning the whole complex dance from the data itself.
That's the idea, potentially bypassing some of those limitations.
So what specific things can this AI model predict about a hurricane or typhoon?
The source material lists the key things forecasters need to know. It can predict the storm's formation, basically, flagging when and where a weather disturbance is likely to organize into a named tropical cyclone.
That's useful. Early warning.
Very. Then, of course, the storms track its likely path, its intensity, how strong the winds will be over time. But also, crucially, it predicts the storm's size and its shape.
Size and shape. Why are those important?
Well, size tells you how large an area is going to be affected by dangerous winds, storm surge, heavy rain. A huge storm affects a much wider zone than a small, compact one, even if their peak winds are the same.
Okay.
And shape influences how those hazards are distributed. Is the strongest wind quadrant going to be on the right side, the left side?
No.
That matters for pinpointing the greatest impact areas. So predicting those 5 things, formation, track, intensity, size, and shape, gives a pretty comprehensive picture for forecasters.
Covered the bases. And you mentioned earlier, it doesn't just give one prediction. You said something about multiple outcomes.
Right, that's another really key feature they mention. Instead of just outputting one single forecast track and intensity profile, like a traditional deterministic model run might, this AI model can generate 50 possible scenarios for a single cyclone at each forecast time step.
50. Wow. So what does that look like?
Imagine looking at a forecast map. Instead of just one line showing the most likely track, or one cone of uncertainty, you might see 50 slightly different plausible tracks fanning out, and maybe 50 different intensity forecasts associated with them.
That sounds complex, but also really useful.
It's incredibly valuable because, like we said, weather is uncertain. A single forecast line, no matter how good the model, kind of hides that uncertainty. Seeing 50 different possibilities, the spread in the tracks, the range of potential intensities gives forecasters and emergency managers a much better handle on the risk.
They can see not just the most likely outcome, but also the plausible worst-case scenarios within that spread.
Exactly, and maybe even some less likely but still possible outlier scenarios. It allows for much more nuanced risk assessment and planning. It's just a richer, more realistic picture than a single prediction.
50 scenarios. Definitely more information to work with. And how far ahead does it try to predict? What's the forecast horizon?
The source says it provides predictions up to 15 days out.
15 days. That's really long range for hurricane forecasting.
It is. And, accuracy naturally decreases the further out you go with any model. But even having a probabilistic glimpse of potential development or movement 2 weeks ahead, that can be incredibly useful for very early, large-scale planning, thinking about positioning major assets, long lead time preparedness measures, that kind of thing.
Okay, so the potential capabilities sound impressive. Unified model, track, intensity, size, shape, probabilistic forecasts out to 15 days. But how did they actually build this? What did it learn from? What's the data diet, as you called it?
Right, because the AI is only as good as the data it learns from.
Yeah.
And the source explains they use 2 main types of data, and critically they use them together.
Okay, what were they?
First, it was trained on a massive atmospheric reanalysis data set.
Reanalysis.
Yeah.
What's that exactly?
Reanalysis data sets are amazing resources. They essentially reconstruct the state of the Earth's atmosphere over many, many years, sometimes going back decades. They do this by taking millions and millions of historical observations.
From satellites, weather stations, planes, ships.
All of that, yeah. Balloons, buoys, everything. And they combine or assimilate all those observations into a sophisticated physics-based weather model. The result is a consistent, long-term, hour-by-hour history of the weather across the entire globe.
So it's like the best possible reconstruction of past weather.
Pretty much. And by training on this massive data set, the AI model learned about the general behavior of the atmosphere, global patterns, seasonal cycles, large-scale features like jet streams, those big steering currents we talked about. This provides the essential global context for predicting where a storm might go.
Okay, so that's the big picture context. What was the second type of data?
The second was a specialized database focused purely on tropical cyclones. This contained the detailed historical records, the verified tracks, the measured intensities, the estimated size, the wind radii for nearly 5,000 actual tropical cyclones observed over the past 45 years or so.
Wow, 5,000 storms.
Yeah. So by studying all those past storms, the model learned the specific characteristics and behaviors of tropical cyclones themselves, how they tend to form, how they intensify or weaken under different conditions, how their structure, their size, and wind fields typically evolve. This historical storm data is key for getting the intensity and the storm structure predictions right.
So it learned the global weather patterns and the specific details of thousands of real storms within those patterns.
Exactly. And the source really emphasizes this point. Training the AI model on these two different types of data together was crucial. It didn't just learn about steering currents in isolation or past storm behavior in isolation. It learned how past storms actually behaved within the specific global atmospheric environments they moved through. That combination was key to improving its prediction capabilities compared to using just one data set alone.
Okay, that makes sense. Learning the context and the specific events together. So how well did this training actually work? Did they test it? How did it stack up against the models already in use?
Ah, yes. The all-important testing and comparison phase. This is where we see the concrete numbers suggesting its potential. The source details how they compared their experimental AI model against some of the leading operational physics-based models used by forecast centers around the world.
Who did they compare it against?
Okay, so for track accuracy, they went head-to-head with ENS.
ENS, that's the big European model ensemble.
That's the one. The Global Ensemble System from the European Center for Medium-Range Weather Forecasts, ECMWF. It's widely regarded as one of the best, if not the best, global weather prediction systems in the world, especially for track forecasting.
So a tough benchmark.
Absolutely. And they tested the AI model's track predictions against the actual verified paths of hurricanes observed by NOAA, the National Oceanic and Atmospheric Administration, during the 2023 and 2024 hurricane seasons, specifically focusing on the North Atlantic and East Pacific basins.
Okay, real-world test cases. What did they find?
The results reported are, well, pretty striking. On average, they found that the AI model's 5-day track prediction was 140 kilometers closer to the storm's true observed location than the 5-day prediction from the benchmark ENS model.
140 kilometers closer. At 5 days out, that sounds like a really significant improvement.
Is it? It is significant, yeah. But the source gives even better context to understand how significant. They point out that this 140-kilometer reduction in the average 5-day track error, well, that level of accuracy is comparable to what the ENS model typically achieves at only 3.5 days out.
Wait, so the AI model at 5 days was as accurate as the leading global model is at 3.5 days.
That's a comparison they draw. Essentially, it suggests the AI model demonstrated something like a 1.5-day improvement in track forecast lead time accuracy.
A day and a half better lead time for the same accuracy level.
Wow. And the source puts that into perspective, too. They note that achieving that kind of 1.5-day improvement in track forecasting skill, historically, through gradual refinements of physics-based models, has typically taken over a decade.
A decade's worth of progress, potentially achieved much faster with this AI approach.
That's the implication from these internal tests. Seeing that magnitude of improvement, basically jumping forward maybe 18 months worth of traditional progress in track accuracy from a totally new modeling paradigm. That's a really eye-catching metric. It underscores the potential scale of this advancement, if it holds up.
That really drives it home.
Huh.
Okay, so a potentially massive leap in track forecasting. What about the other half of the problem, intensity? How did it do there?
Right, the intensity forecast. For that comparison, they benchmarked their AI model against HAFS.
HAFS. That's the Hurricane Analysis and Forecast System.
Correct. That's a leading regional high-resolution physics-based model developed specifically by NOAA, the National Oceanic and Atmospheric Administration. It's designed precisely to capture those complex small-scale storm processes we talked about that govern intensity changes. So it's a specialist model for intensity.
Okay, so comparing the AI against the specialist intensity model, what was the outcome?
According to the internal testing results in Source, the experimental AI model actually outperformed the average intensity error of the HAFS model.
It beat the specialist intensity model.
In terms of average intensity error in their tests, yes. So the findings were twofold. A significant improvement in track compared to a top global model, and better intensity accuracy compared to a leading regional high-resolution model specifically built for that purpose.
And all from that single unified AI system.
That's the remarkable claim. It seems to suggest that, at least in these evaluations, the AI approach was successful in learning to handle both the large-scale steering factors for track and the fine-scale internal physics for intensity simultaneously, overcoming that traditional trade-off.
That is seriously impressive if it translates to consistent real-world performance.
Exactly. The source also mentions briefly that preliminary tests for predicting the storm's size and wind radii showed results that were comparable with the existing physics-based baseline models.
So promising across the board, basically.
The initial internal results certainly paint that picture. They also note, importantly for the scientific process, that visualizations comparing these track and intensity errors are available for other experts to scrutinize. Transparency is key here.
Absolutely. Okay, so the internal tests look fantastic on paper, but as you said earlier, the real world is the ultimate proving ground. And getting buy-in and validation from the operational forecasters, the people who actually have to use this stuff to make critical decisions, that's essential.
Couldn't agree more. You can have the best model in the lab, but if the operational community doesn't trust it or can't effectively use it, it doesn't help anyone when a storm is actually threatening. That brings us to the partnerships they highlighted.
Right. Who are they working with to validate this?
The source emphasizes several key collaborations. Probably the most prominent one mentioned is with the U.S. National Hurricane Center, the NHC.
Okay. The folks who issue the official forecast for the Atlantic and East Pacific?
Exactly. They are the operational experts on the front lines for those regions. The source says the NHC has been scientifically validating the AI approach and its outputs.
What does scientifically validating mean in practice?
It means their expert meteorologists are looking closely at how the AI model performs, comparing its predictions against what actually happens with real storms, assessing its strengths, its weaknesses, its biases under different scenarios.
And are they just looking at past data or?
No, this is the really crucial part. The source states that NHC expert forecasters are now seeing live predictions from these experimental AI models.
Live, as in during this current hurricane season.
Yes. They're seeing the AI output streams on their internal forecasting systems right alongside all the traditional physics-based model guidance and the real-time satellite and aircraft observations they use every day.
Wow. So the human experts making the official forecast decisions at the NHC are actively looking at this experimental AI guidance right now when they're analyzing active storms.
That appears to be the case based on the source material. It's being treated as another tool, another piece of guidance for them to consider in their complex forecast process.
What's the hope there?
The hope, as the source puts it, is that having access to this potentially very skillful AI data will provide valuable insights. Insights that could help the NHC forecasters refine their official forecasts, maybe improve the accuracy, or potentially provide earlier or more confident warnings about the hazards. It's a really critical phase of real-world, real-time evaluation.
So the performance of this experimental model this season, under the eyes of the NHC experts, is really make or break for demonstrating its practical value.
Absolutely. It's the ultimate test. Another major collaborator mentioned is CIRA, the Cooperative Institute for Research in the Atmosphere. They're based at Colorado State University.
Right. CSU does a lot of hurricane research.
They do. And a team there, led by Dr. Kate Musgrave, conducted an independent evaluation of this AI model.
An independent look. What did they find?
According to the source, Dr. Musgrave's team concluded that the model demonstrated comparable or greater skill than the best operational models for track and intensity.
So another group, looking independently, came to a similar conclusion as the internal Google tests.
It seems so, yes. That kind of independent verification from a well-respected research institution like CIRA adds significant credibility to the initial findings.
That's important. Do they say anything else?
Yes, and it echoes the point about real-time performance. Dr. Musgrave is quoted saying her team is looking forward to confirming those results from real-time forecasts during the 2025 hurricane season. So, again, reinforcing that while the historical testing is compelling, proving its reliability now in ongoing operational settings is paramount.
Makes total sense. Compelling results in testing, now under intense scrutiny in real time by the experts who live and breathe this stuff. Were there other partnerships mentioned?
Yeah, the source also lists collaborations with the UK Met Office, the University of Tokyo in Japan, a private Japanese company called Weather News Inc., and other sort of trusted testers globally.
So getting feedback from different regions, too.
Exactly. And that's important because tropical cyclones can behave differently in different ocean basins due to varying environmental conditions. Testing and getting feedback from experts dealing with typhoons in the Pacific or cyclones in the Indian Ocean provides a more complete picture of the model's strengths and weaknesses globally.
So the overall goal of all this collaboration is?
It's about gathering crucial feedback, as the source emphasizes. Feedback from the weather agencies, the emergency managers, the people who have to make life or death decisions based on forecasts. They need to understand how this new AI technology can best fit into the existing forecast process, how it can genuinely enhance the official forecasts, and ultimately how it can help inform better decisions to save lives and protect property. It's about bridging the gap from research to real-world operational impact.
It definitely sounds like the focus is on practical application, getting this tool refined and potentially integrated where it can do the most good. How are they making this technology more broadly accessible for experts to look at and evaluate?
That's where a platform called Weather Lab comes in. The source describes it as an interactive website that Google DeepMind and Google Research have launched. It seems to be the main public-facing portal specifically for the expert community, where they share these experimental AI weather models.
Okay, Weather Lab. What does it actually offer? What can experts find there?
It provides access to both live, real-time predictions and also historical forecast archives from several of Google's experimental AI weather models. This includes the specific tropical cyclone model we've been focusing on, but also others like WeatherNext Graph and WeatherNext Gen, which might have different strengths or focuses.
So they can see the AI output.
Yes. And crucially, Weather Lab also displays predictions from well-established physics-based models right alongside the AI ones. They specifically mention showing output from ECMWF's ENS ensemble, the European model we talked about, for direct comparison.
Ah, so you can see the AI forecast next to the traditional model forecast for the same storm.
Exactly. That side-by-side comparison is critical. It allows experts from weather agencies, research groups, private companies, wherever, to directly evaluate the AI model's performance against the models they already know, use, and trust. They can see how it behaves, where it agrees, where it differs, and start to build an understanding of its characteristics.
So it's a platform for transparency and comparative evaluation within the meteorological community.
That seems to be a primary goal, yes. And transparency is further supported because, as the source highlights, Weather Lab also provides an archive of historical predictions from these models, apparently going back over 2 years.
An archive, so you can look back at past storms.
Yeah, and researchers or other experts can actually download this historical forecast data. This allows them to conduct their own independent, in-depth evaluations of a model's performance over longer periods, across different storm situations, and in all the various ocean basins around the world. That open access to historical data is really important for building wider scientific confidence and validating the technology thoroughly.
Okay, so it's a place to see live runs, compare models, and download historical data for deeper analysis. How does using this platform actually help, say, an emergency manager or a forecaster on a practical level when a storm is brewing?
Well, the source suggests that by using Weather Lab to explore and compare the predictions from the different models, both AI and physics-based forecasters can get a more holistic view of the situation.
Looking at everything together.
Right. Seeing the AI model's output, maybe those 50 probabilistic scenarios it generates, alongside the ensemble plumes from traditional models like ENS, and comparing that with the latest satellite imagery and aircraft data, it gives a more robust understanding of the potential track, the potential intensity range, and importantly, the uncertainty surrounding the forecast.
A richer picture to inform decisions.
Exactly. The source notes this helps agencies with better preparation. They can develop contingency plans based on the range of plausible scenarios, not just a single forecast line. It can help improve how they communicate the risks to the public, talking about likelihoods and possibilities rather than just one outcome. And ultimately, it supports more informed decision making about everything from evacuation orders to where to pre-position emergency crews and supplies. It's a decision support tool.
It sounds like a potentially very powerful addition to the forecaster's toolkit for improving situational awareness.
Huh.
But, and this feels like a really important but, these are still experimental models, right?
Hmm.
What are the caveats here?
Absolutely critical point, and the source material is very clear about this, thankfully. It includes a prominent and essential disclaimer. Weather Lab is a research tool.
Okay, say that again. A research tool.
Yes, not an official source for warnings. The live predictions shown on Weather Lab are generated by models that are still explicitly described as being under development.
Experimental. Not finalized.
Yes.
Not operationally certified in the formal sense.
Precisely. These are experimental models. Their output should never be taken or used by the public, or anyone really, as official weather forecasts or warnings.
This cannot be emphasized enough, especially for people in hurricane-prone areas who might stumble across this site.
It really can't. The source makes it absolutely explicit. For official weather forecasts and warnings that you should use to make safety decisions, you must refer to your designated local meteorological agency or your National Weather Service.
Like a National Hurricane Center in the U.S.
Exactly, or the equivalent official body in whatever country you're in. While these AI models are exciting and clearly valuable tools for experts to evaluate and potentially incorporate into their thinking, they are not the final authoritative word for public safety.
The official forecasts and warnings still come from the human experts at the recognized agencies.
Yes. Those experts synthesize all the available information data from multiple traditional models, ensemble systems, satellite observations, aircraft reconnaissance, their own experience and expertise, and now, potentially, insights from these experimental AI tools to issue the definitive public advisories and warnings. The responsibility rests with them.
That's a vital distinction. The potential is huge, the research is exciting, but always rely on the official sources for safety decisions.
Couldn't say it better. The AI is adding new data points, potentially very valuable ones, to help inform those human experts, but it doesn't replace them or the official warning system.
Okay, so let's try and pull all this together then. Thinking about the big picture, what's the real significance of this development? Why should you, our listener, care about this experimental AI hurricane model?
Well, if we recap the main points, this AI model shows real, tangible promise in tackling that long-standing challenge in hurricane forecasting.
Yeah.
Getting both the track and the intensity right with high accuracy from a single system.
Overcoming that trade-off.
Right. The internal tests they presented showed results that were, frankly, remarkable, especially that potential 1.5-day leap forward in track forecast lead time accuracy at the 5-day mark. That's the kind of jump that historically has taken many years, even a decade or more, of incremental progress with traditional methods.
And it wasn't just track, it also showed better intensity performance than a specialist model in those tests.
Correct. And maybe most importantly, this isn't just happening in a lab anymore. Leading operational forecast centers like the NHC and top research partners like CRA, they are actively looking at this model's performance right now in real time during this current hurricane season. The validation process is underway in the real world.
So connecting that back to the listener, back to that $1.4 trillion damage figure, back to the human impact, why does this specific development matter?
It matters because of the direct link between forecast improvements and real-world outcomes. Even seemingly small gains in accuracy, getting the track just a bit better, predicting rapid intensification just a little sooner, or extending the reliable forecast lead time by half a day or a full day. Those improvements can have massive positive consequences.
How so?
Better preparedness, more time for effective evacuations, which saves lives, more efficient staging of emergency resources, getting crews, supplies, shelters ready in the right places, better communication of risk to the public. It all contributes to reducing the devastating loss of life and the enormous economic disruption these storms cause. This AI model, based on its initial promise, holds the potential to deliver those kinds of tangible improvements.
And this whole development, it feels like it fits into a bigger picture, a larger trend we're seeing with AI, doesn't it?
Oh, absolutely. This is a really compelling example of how artificial intelligence is increasingly being applied to tackle really complex scientific problems and major societal challenges. The source material itself frames this work under Google's broader umbrella of AI for climate and sustainability.
We're seeing AI used in drug discovery, finding new materials.
Exactly. Optimizing energy grids, understanding complex biological systems, and now significantly improving our ability to predict and prepare for extreme weather events, which, let's face it, is becoming ever more critical in the context of a changing climate.
It is genuinely exciting, I think, to see this incredibly powerful technology being pointed at problems that have such a direct, tangible impact on people's lives, on community safety and resilience.
It really is. It represents a powerful new tool, a new way of thinking being added to the scientific arsenal. It offers the potential to accelerate discovery and boost our predictive capabilities for phenomena that have historically been very, very difficult to forecast accurately.
Okay, so as we wrap up this deep dive into AI hurricane forecasting on Meteorology Matters, here's maybe a final thought for you, the listener, to mull over.
Go for it.
If, and it's still an if based on this season's performance, but if these experimental AI models continue to prove their worth in real-time evaluations, how might this fundamentally change the dynamic inside the forecast offices, the control rooms where those critical life-saving predictions are made? How do you see human expertise and AI guidance best working together in the future? Will the AI provide the baseline and the human fine-tunes, or something else?
That's the huge question, isn't it? The human-machine collaboration aspect.
And maybe take it a step further. Could this approach this idea of learning extremely complex dynamics directly from vast data sets, could that be applied effectively to predicting other chaotic, dangerous natural events that we still struggle with? Things like, I don't know, major earthquake aftershock sequences or the unpredictable behavior of large wildfires.
Those are fascinating and really important questions about where this technology might lead. Predicting complex natural systems is one of science's grand challenges.
It seems like the potential is there, but figuring out the right way to integrate it, validate it, and rely on it is the next big step.
Absolutely. The developments we've discussed today are definitely a significant stride forward. They open up really exciting new possibilities for prediction, but they also highlight just how important that careful ongoing validation process is, how crucial it is to figure out the best ways to integrate these tools, and importantly, they underscore the continuing, irreplaceable role of human expertise in interpreting the outputs, understanding the limitations, and making the final, responsible forecast decisions.
Couldn't agree more. Well, that has certainly been an enlightening look at a potentially transformative technology in the weather world. Thank you for joining us for this deep dive on Meteorology Matters.
My pleasure. It's a fascinating field right now.
And hey, if you want to keep up with the latest in weather forecasting, especially tropical cyclones, you should definitely follow meteorologist Rob Jones. He shares great insights.
Where can people find him?
You can find him on Instagram. His handle is @meteorologist. On TikTok, he's @tvmeteorologist. And over on YouTube, just search for Rob Jones Hurricane, ROBJONES Hurricane. You'll find his channel there. And he also has a playlist for all the Meteorology Matters podcast discussions.
Good stuff. Worth checking out.
Definitely. All right, that's all for this time. Until our next deep dive, stay informed, stay curious, and please stay safe.